The topic of my course is at the intersection of several fields: algebraic geometry, a little bit of representation theory and combinatorics. Since Alfred is speaking after me, I'll try to present the ideas that do not interfere with his talk, so you're not going to listen to the same story twice. So I'll give essentially the idea from the geometric perspective, and he will explain how they fit together with an elegant question in representation theory. So the style of the presentation is, I'm trying to give very much like a small course. So I know that this is not the background of most people here. So the idea is that if you take notes, you can actually learn the topics. I'm going to try to give something that is self-contained. First of all, what is an elliptic fibration? So an elliptic fibration is an algebraic variety. So that means it's a geometric object that can be described using only polynomial equation. And the fact that it's a fibration means that you have a base on a surface. So you have the following structure. So you have a base manifold B, and on top of every point of that manifold, you have what is called a torus. So a torus is an object that everybody sees when they take their first class in topology. So often it's described as taking a rectangle and identifying two opposite sides of the torus. So if you do that, there is a few invariants that you can consider. So first of all, it's very fine to say that one of the length is normalized to 1. And then all your torus is completely described by telling what is this number as a complex number. So basically you see that there is an angle here, and the length is totally controlled by this variable tau. And it's enough to ask for the imaginary part of tau to be positive, which means basically you are on top of the axis you use as your base. So once you do it, a natural question to ask as a mathematician is, if I take two tori with different tau, how do I know that they correspond to the same object? When is the torus isomorphic? So this is resolved by considering the following symmetry. So you can start with a torus defined by tau and send it to another torus defined by this Mobius transformation under requirement that ABCD belong to SL2R. So for this talk, actually, let's work already with the discrete version. So let's work with SL2Z. So this is the group that is the center of many questions of number theory. So elliptic curves, they play an important role in number theory. So for example, in the proof of Fermat's theorem, extremely relevant. I know there are some cryptographs that are here. And in cryptography, using elliptic curve is also like a technique that secures, for example, transaction on your cell phone and when you contact your bank through the internet. So two tori will correspond to the same object if tau that we can think of as the complex structure is related to the other tau by this Mobius transformation. So once you have a fibration, what is interesting is that you can have singular fibers. So asking what is a singular fiber of an elliptic fibration is an extremely interesting question to ask in algebraic geometry, because it brings you to discover aspects of the property of variety that are usually not so easy to see, but in this case they're very visual. So I'm going to first draw an example of a degeneration. So here I take a torus. So I learned in the US when people want to make tori accessible, they always say it's a donut. So donuts are not things that we eat where I grew up. So I grew up in Congo and in Europe. So for you guys, it's a donut. So now you take a circle in your donut and you consider a line that controls the radius of that circle. So eventually, you can go to a degeneration where basically you took that circle to become like a point. And this is an example of a singular tori. So such a curve is called a nodal curve. So the reason why I call it a curve is that in algebraic geometry, we work over the complex number. And so when we talk about dimension, you have to divide by 2. So a torus is a surface if you think of real coordinate, but if you think in terms of complex numbers, it's just like a curve. So this is an example of a nodal curve, and in the notation of Kodaira, this is denoted a curve of type I1. And so now I'm going to make a generalization of this that will show you that the theory of elliptic fibration is naturally connected to some aspect of group theory of representation theory. So consider the following situation where I start with a tori, but this time I take more than one circle. So I take a bunch of circles, and then I shrink all these circles at 1 to a point at the same time. So what you get is going to have more or less the following shape. So it looks like a collection of spheres that touch each other by a point. So I'm going to draw the same structure here, where basically each of these circles represent one of these curves, and I draw a line when they are connected by a point. So now, if, like Alfred Noel, you are an expert in representation theory, a diagram like this is something that you recognize automatically, because this is called like a Dynkin diagram. Of type IN, when n is, of type AN minus 1, when n is a of node. So for example, a theory like SU3, the group SU3 has a Dynkin diagram of this type. So those that form a loop like this are usually called extended. And the usual Dynkin diagram is when you remove one of the nodes. So it means that the moment you start asking yourself what is like a theory of elliptic fibration with degeneration, you naturally encounter this type of diagram. And so in the string theory context, for example, which I'm not going to talk too much, this is used to generate specific gauge theories. So in general, the singular fibers of an elliptic fibration are not always that simple. They can be more difficult to visualize, and I'm going to give the full list on this board. So Kodaira is a very famous algebraic geometer, or just a geometer, because he was interested in also non-algebraic spaces. And I think it was around 1960 to 1963, he was trying to answer the following question. What happens if I try to classify all type of surfaces? And there is an invariant that he used, which is called the Kodaira dimension, that end up playing an important role. And among all surfaces, there was a special case that needed to be studied on the side. And that special case is the case of elliptic surfaces. So it means an elliptic fibration over a curve. And for this type of fibration, you can actually give an explicit classification of the singular fibers. And they come with the following shape. So we have type 1, which is the nodal curve, which here I represented like this, but here really what I mean is you have a curve that intersects itself. So usually we just draw it like this. It looks a little bit like an alpha. And the main point is to see that at the point of intersection, you have two tangents that are distinct from each other. The next type of singular fiber are very difficult to see, starting from a torus. And this is called the cuspidal curve. And the cuspidal curve is a degeneration of the nodal curve when the two tangents coincide. So it looks a little bit like that. So then there are other type. You have the fiber of type 3. And the fiber of type 3 is just like two curves that touch each other, to point of tangency. So they basically are tangent at the collision point, which has multiplicity 2. Then you have the fiber of type 4, which consists of 3 curves that intersect each other at the same point. So these 4 that I draw here are of a special type because they're not naturally associated with a Dynkin diagram. The followings are much more interesting. So we have type IN, which is very much the type that I draw here. So it's a collection of n curves, and they touch each other along like a point. And then you have I star n that has the following structure, where the curves in the middle all have multiplicity 2. So what is interesting with these two types is that you naturally associate them a structure using a Dynkin diagram. So this is Dynkin diagram of type AN-1, and this is a Dynkin diagram of type D4 plus n. So example of group that are defined by this are the orthogonal group, like SO10, SO8, all those that have even rank. Actually, I'm going to continue here. Then the next 3 that I'm going to draw are the exceptional ones. So you have the fiber, let's start with 4 star. And this is related to the extended Dynkin diagram of type E6. You have the one of type 3 star. Which is related to the Dynkin diagram of type E7. And finally, we have the the Kodaira fiber of type 2 star that is related to the Dynkin diagram of type E8. Yes. So there is a lot of beauty hidden on this picture. So first of all, Dynkin diagram, they appear across all mathematics. They are used to classify some regular object in classic geometry that was already known to the Greeks. They are used to classify, obviously, a group on the Lie algebra. They also use in representation theory. And they have a lot of little details that always come at a surprise, but it's usually related to some very deep mathematics. So for example, if you look at the multiplicity I give to this node, you will notice that they satisfy the following condition. If you take one of this number, it's always the sum of those that surround it divided by 2. So for example, 2 would be 1 plus 3 divided by 2. 3 is 2 plus 4 divided by 2. 4 is 3 plus 2, which is 8 divided by 2. And properties like that end up even playing an important role when you study an object like the monster group. So far, you should say the following thing. So how is it you tell us that this is algebraic geometry, but what we have seen so far is just a collection of pictures. So what I'm going to do next is I'm actually going to do a little bit of algebra to show you how some of this curve can actually come out as a result of an extremely simple algebraic computation. So I have to choose one of these curves to play with. So I think I'm going to go with type 4. So basically, I'm going to describe an elliptic fibration that has a singular fiber, and through a little computation, we'll see that we will end up exactly with this fiber. So when you think of an elliptic curve from the geometric point of view, like the algebraic point of view, you have the following definition. So an elliptic curve, this is like a curve of genus 1. With a rational point. So it means that if you write a curve of genus 1, you also need to be able to find a solution which is rational in the field under which you define your curve. So now there is a very beautiful theorem which is an application of the Riemann-Roch theorem. So the Riemann-Roch theorem tells you how you can have like a control on the property of function you can define on a curve. And one of the, at least in my class, I always do it as a p-set problem. I want my students to be able to show that if you have a curve of genus 1 with a rational point, you can always express it by a cubic equation, which is called a Weierstrass model. So you have the following theorem. An elliptic curve is always isomorphic to a Weierstrass model. So now this theorem is useful if I tell you what a Weierstrass model is, so that's what I'm going to do next. So a Weierstrass model is an equation defined in the projective plane. So we work in the plane P2. And it's a cubic equation of the following form. So P2 is the projective space. So what it means is that it's the set of points x, y, z that belong. Let's say that our field is the field of complex number. So you take all triplet of complex number, but you have to remove the origin, and you have to rescale it of using the following symmetry. So x, y, z would be equivalent to lambda x, lambda y, and lambda z. So in other words, you just look at the direction you have in the plane, and the scaling does not matter. So all the equations that you write in a projective space have to be homogeneous equation. So now a cubic equation that is a Weierstrass model has the following form. where basically here f and g are just like complex numbers. So as you can see, the equation is cubic in every of the variables we have. But if it's just like a cubic equation in P2, the only thing we know is that it has genus 1. To be elliptic, you also need a rational point. And here, the rational point is given explicitly by the point x equals z equals 0. So if you look at that equation, you see that it satisfies the equation. And any curve of genus 1 can be expressed exactly in this form. So now there is a little bit of a twist. For this to actually be a smooth curve, you need to satisfy the following conditions. So let me call this curve E. E is not for my last name, it's for elliptic, just in case. So E is smooth if and only if we have a discriminant locus which is different from 0. And the discriminant has a very simple definition. Up to a constant, you can take it to be 24 4f cubed plus 27 g squared. So if you choose f and g that are not solution of delta equals 0, you find yourself a smooth elliptic curve. Okay. So there is also, like, you can even characterize the class of the curve up to an isomorphism. And so that invariant can be obtained by just looking at what are the scaling that preserve the equation. But here I'm just going to write it for later details, for later use. So this is called the J invariant of the elliptic curve. So if I have two elliptic curves that have the same J invariant, they are always isomorphic to each other. And here I'm actually working over the complex. So now we can actually now do some detailed study of elliptic curves and their degeneration by turning this into a fibration. So far, as you can see, it's just a curve. So if I want it to be a fibration, what I should do is I should use some base manifold. So here I'm going to use just like a line that I'm calling the t line because I parameterize it by a variable t. And now for each point of that line, I want to put some elliptic curve that depends on t. And the definition of the curve that I will use is the following. So this is my elliptic curve that basically moves for every point of t, I have a different curve. So now it's pretty easy to show that that curve that I wrote actually has a singularity when t is 0. So to find singularity, you just look at the locus when all the partial derivatives are 0. And this happens exactly t equals 0. So this is a very easy theorem. I'm going to write it with equalities, x, y, t equals 0. So if there is a singularity, now the problem is how do you deal with the presence of a singularity? So in algebraic geometry, there is a whole theory which is called resolution of singularity. That tells you basically how you can clean up a singularity so that you end up with something smooth. And it happens that Princeton is like one of the leading institutions for the study of resolution of singularity, mostly actually Princeton University more than the institute. Did I say something awkward? No? Okay. So the idea of resolution of singularity is very simple. And I always like to think about it as a good example to show people how you actually think about problems in mathematics. You have a singularity, you want to remove the singularity. So what does it mean to remove a singularity? One way would be to say that it would be nice to have another space that looks very close to my original space, but it's just different at the place where I have the singularity. And the way you do it in algebraic geometry is to say, let's say you have some space X, and you want to resolve its singularity. So it means what you do is you define a map for another space to X. So X can look like the shadow of the space Y. And then you ask the map to satisfy some condition. So the condition you ask are the following. First of all, you want the space Y to be smooth, meaning that you basically remove the singularity. The second condition you want Y, you want the map phi to be an isomorphism away from the singularity. So in other words, if I consider all the points that are smooth, Y and X are exactly the same space. But then Y is actually smooth, while X is singular. So now the problem with this definition is that there is no theorem of, let's say for Y there were no theorem of existence, no theorem that tells you that the solution is unique. Hironaka finally wrote a theorem of resolution of singularity that tells you that for every singular space, you can find a smooth space that satisfies this condition. Actually, he gave even more detail. But on the other hand, the solution is it's not always unique. So it means that you can find yourself in the following case, where you start with some space X, which is a singular space, but then you find two different resolutions of X. And both of them have smooth spaces. So one of them might look like X, but you remove the singularity and you replace it with some like big hat. And the other one looks like X, but you replace the singularity with the Eiffel Tower. So both spaces end up being smooth, but they are different because the only place where they can be different, you did put something different. And birational geometry, among other things, is related to the study of such objects. So objects that kind of look the same, but they are different in a certain sense, but they can find common ground. That's an idea that you can also apply to politics, I guess, but these days it's not very popular. So let's go back to the case that we are considering. So we have this specific space, and I want to see how you can think of the resolution of that space. So if you think about it, it's very tricky. How do I find like a map which is actually an isomorphism away from a specific point? So I'm going to give you an example, starting with the affine plane. So I take the affine plane with coordinate x and y. And what I want to do is I want to define a space which looks exactly like the affine space except at the origin. So to do that, I will add something that is actually huge. I will add a full curve. So I will take y to be defined as a squared times a projective line, and my projective line will have coordinate alpha, beta. But then I want to quotient this with an equation, and the equation I consider will be alpha y minus beta x equals 0. So now, if you think about it, adding the space A1 has increased the dimension of the space, But because I also put a constraint, I actually preserve the dimension. And so now the real question is, why is this an isomorphism away from the origin? And the solution is very simple. Since alpha and beta are coordinates of a P1, by definition, alpha and beta cannot be 0 at the same time. So you have two possibilities. Or you have alpha different from 0, or you have beta different from 0. If alpha is different from 0, then you can explicitly say what is y. So you will have that y would be given by this. And if beta is different from 0, you can actually solve this for x. And you will have that x is given explicitly by alpha, beta, y. Because of these two possibilities, you see that as long as, well, actually I did it the other way around. So if I am away, let me do it this way, away from the origin, I need to have x different from 0 or y different from 0. If x is different from 0, I can solve for beta. And if y is different from 0, I can solve for alpha. So altogether, the extra space that I added doesn't really matter when I am away from the origin, because I can always choose a point of A2 and give explicitly a unique point in P1. But then what happened is at the origin, when I sit at the origin, this equation is automatically satisfied. So it means when I am exactly at the origin, there is no constraint, and I just get the full P1. So in other words, what I've done is I replace A2 by A2 with a sphere replacing the origin. So this is called a blow-up. So one way you can describe the blow-up more explicitly is by just doing a simple rescaling. So you can say that the blow-up is the same thing as saying that x and y are just the same thing as alpha and beta, rescaled by some scaling that you call E. So now, if you do that for the curve that I started with, the following will occur. So you start with this equation. I'm writing it in a patch. And then you rescale the center of your singularity. I'm going to write the new variable with a bar, and the parameter would be E1. With the condition that this free parameter lives in the projective space P2. So then, if you implement this inside the equation, the first thing you see is that you can actually factor a power of E1. So think of this equation as this, and when you rescale by E1, there is a factor of E1 square, of E1 that comes out. So it means you have two components in your curve. And what you do is you basically ignore the first component, and this is your new equation. But then the geometry of this equation is totally different than the previous one, because before the singularity was a t equals 0, but now t is replaced by t bar E1 equals 0. So it means that all of a sudden what used to be just like a smooth curve that is irreducible is now composed of two components. And if you look at the first component, so if you look at E1 equals 0, you see that this part disappears. And you just have a quadric. Whereas when you look at t equals 0, you just have what is actually a normalization of a curve. So now, this quadric, you can actually factorize it if you allow yourself to take the square root of b. And altogether, the first equation represents two lines that meet at a point, and the third one is just another line that meets it at its intersection, and you retrieve the fiber of type 4. Okay, so this is like a pretty simple example of resolution of singularity, and you can now ask yourself the following geometric question. What happens if you want to resolve the other Kodaira fiber? So now I have an announcement. This talk is actually going to take 6 hours, and we're going to go through the resolution of all of them. So no, seriously, each Kodaira fiber has only one way to be resolved. And as long as your base is one-dimensional, this is canonical. So all of them have nice resolution of this type. Even when there are different roads to build that fiber, they are all isomorphic to each other at the end. So the real question is, what happens when the base is of dimension greater than 1. So if you have a base of higher dimension, what happens is that you can have different types of singularity that collide each other. So let's say your base is a surface. Over each point of the surface, you have a smooth elliptic curve. But then your discriminant locus can have two components, over which you can have different types. So for example, one type might be two curves that intersect like this, and the other one is a triangle. And the question is, what happened at the collision of these two? So if you think about it, this is like the algebraic geometry equivalence of a car accident. Okay, so you have like two guys that go for each other, but they do meet at the intersection. So at the intersection, something has to happen. And so for this case, I can actually tell you what the solution is. What you will have is just like a pentagon. And the example I draw here is not an innocent example. This is a geometric way to engineer a part of the standard model that represents like a usual way we do physics. So this fiber corresponds to a Dynkin diagram, an extended A1, whereas this one corresponds to an extended A2. In terms of group, you will have an SU2 group times an SU3 group. So this collision geometrically realizes everything we know about the standard model of particle physics, SU2, SU3. So at the collision here, you can even retrieve the representation that represents like the quark and so on. So when I draw it like this, it seems as if the solution was unique. But actually, what we're talking about, the existence of multiple solutions, end up playing an important role. For this geometry, remember I gave you a picture when you have a singular variety, and you can have two resolutions that are connected to each other. For this geometry, you do not get two resolutions. You actually get like a total of 6. And the way they are related to each other is the following. Okay, so don't confuse this with a classical Dynkin diagram. So each of these represents a different geometry. So you have like Y1, Y2, Y3, Y4, Y5, Y6, Y7, Y8. So there are 8 of them. And what this line draw are basically transformations like this. They all correspond, they can all degenerate to the same singularity. And these are what is called like a flop. So it's a birational transformation, so it means it's not a well-defined function. There are places where the map is not well-defined, but you do need places where the map is not well defined for the geometry to be different from each other. So you can basically flop from one space to the other, and the full graph of this flop has the following structure. So usually, in order to get a picture like this, you have to do different things. So first of all, you need to show existence of every single one of this geometry. Then you need to show that this geometry can actually transit from one to the other. And then you have to show that there are no other possibilities. So it's an extremely difficult geometric question to answer. And it happens that physicists have found a way to actually predict the result without doing much computation. And so this is actually the last line of the title. The IMS potential is for Intrigilator-Morrison-Seiberg. So Nati Seiberg is a professor of physics who is a member, one of the most celebrated members of the institute here. He was there even over lunch. And so by solving a physics problem, they propose a function that very much characterizes this type of geometric consideration. The data that characterize that function is the following. So you need to give, like, let's say, a Lie algebra. And you're not surprised to see a Lie algebra appearing because in our case, we have this diagram that can be associated to Lie algebra. But you also need a representation of the Lie algebra, and the representation has to do with what happens at the collision, and it's going to be too complicated to explain how the collision gives you a representation. And then the Lie algebra is characterized by the roots, and the representation is characterized by the weight of the representation. And what the potential does, it gives you like a cubic function that depends on this variable, but then the function is not actually continuous everywhere. It has singularity over some hyperplane. So now, so the IMS potential is singular along some hyperplane. Extend it with new nodes that take the following form. And that prediction was based on the use of the Intrigilator-Morrison-Seiberg potential. So first when they did that, we were like, you know, these are just physicists. They don't know what they're talking about. And so we tried to disprove that these guys actually do not exist. And after a lot of effort, we could actually construct each one of the missing geometry. So when you talk about it in the Harvard Math department, everybody's shocked because, you know, I did it with Yao, who is a well-celebrated field medalist, and finding this sixth geometry took us like an year of work. And thinking that we would miss, that us would miss something was pretty shocking, but we did miss something. And physicists could tell you that exactly what is it that you miss. They could even tell you what is the structure of the singular fiber for each one of these nodes, but they don't know how to construct that geometry. They just know it using some string duality. And so basically that's what is really exciting about this area, is because when you try to understand geometry, often you try to talk to something that doesn't talk back to you. You try to touch the geometry, and then when you try to grab it, it goes left. When you follow it, go right. And sometimes you only see one leg of that geometry and not the other. So you really don't really have a vision of what is going on. And then you talk to people who have a totally different point of view of these. They talk about particles, they talk about all these things, but somehow they know exactly what is supposed to happen, but they don't know how to construct it. So the natural thing is to combine these two visions, so to take the idea from physics as conjecture, and then to try to formally prove it. So these are just like examples. Because SUN theories are so important, a natural question to ask is the following, and here I'm connecting with the talk of Alfred Noel. So in general, if you take SUN and you take this representation, how many chambers are you supposed to get? This is an answer that was already solved by Dave Morrison and his collaborator. But then, as I told you before, this geometry, they have, for example, this wall in common. How many walls do you see? How many intersections of walls do you see? So this is a combinatoric problem. I give you a collection of hyperplanes, they intersect, and I ask you to count the dimension of intersection for fixed dimension. And if you think about it from the point of view of geometry, this is a question about counting the number of partial resolution of a very complicated geometry. It's like a non-tractable problem. However, we could find a solution, and the solution not only can be written down explicitly, but is even relatively simple. So SUN, there is a trace condition on SUN. So you can think of a simpler theory, which is just like UN, with exactly the same representation. And for this case, you can even show that the prediction could be expressed as a rational function. So rational functions are the simplest function you can think of because they are just the ratio of polynomials. So thinking that a geometry as complicated as that can be described, at least its birational aspect of its birational geometry, can be all contained in simply a rational function is something that is really mind-blowing when you really suffer. That's why I wanted to do the explicit resolution of a stupid singularity, so that you have the feeling that this is actually kind of something annoying to do. It is kind of annoying. Yes? Sorry? The coefficients are numbers, integer numbers. Yes. Because it's a counting function. It's a generating function. And I think Fred will actually write it. He has slides, so it will be written explicitly. So, okay, so I'm going to stop here for my talk. So my conclusion would be to give the line forward. So together with my student, we are trying to write, so far we have done some important cases one after the other, but the next step would be to try to write the full theory with a collection of theorems. So we are working on it. And the techniques that allow us to do this are the technique of birational geometry. So we try to avoid writing explicit equation and try to think about this in a more abstract way, but that still catch all the information about the fact that you have some curve and you have some hyperplane. And the theory of birational geometry that is relevant for this is called Morris theory. And so last week, the position I have at Harvard is called Benjamin Pierce. And last week it was the 100 years anniversary of Benjamin Pierce. So all the Benjamin Pierce alive, they came for the same conference. And in particular, Maury, who used to be a Benjamin Pierce, together with Andrew Wales as well, they gave talk. And I think Patrick was in, it was really amazing to see that a lot of the things that he talked about are things that somebody who works on particle physics at the Institute will totally relate to. They just use different words for it. And so the reason why this work could be done in count is because all of us have a different background. And so if sometimes you don't just talk to people who do exactly what you do, but you talk to people who do something a little bit different, magic can happen. And my collaborator here proved that interesting collaboration can happen starting from counts. Thank you very much.